Welcome back, everybody. We'll get right back into the end behavior of exponential functions here. We left off the last video understanding that our classic exponential function is increasing over its entire domain, and that domain is all real numbers, from negative infinity to positive infinity. We also determined then that this graph is not bounded to the right, nor is it bounded above, which means that as x approaches infinity, f of x, the function values or the y values, also approach infinity. But we are posing the question, what happens as x goes off and becomes a much larger and larger negative number? As we look at this graph, it certainly looks like several points with x values less than, say, 3, all seem to lie right along the x-axis. That is to say, it looks very much like all of these points have a y value or a function value of 0. But if we take a closer look at those negative x values, we actually see that zooming in on the negative x values gives us a graph that kind of looks a lot like the exponential graph itself. It looks a whole lot like several of these values are right along the x-axis. But that table of values that we put together for negative x values, and which I've written down here onto this graph, shows us that that's not quite the case. Though above, it looked like an x value of -1 corresponded with a y value of 0. Zooming in allows us to see that that -1 x value has a function value of 1/3, and -2 a function value of 1/9, and so on down to the last value that we put in our table, -8, which has an associated y value of 0.00015. Well, there are a couple of things that we should notice here. One, though it looks like this graph seems to lie on the x-axis at some point, as we zoom in, we see that no, in fact, it doesn't lie on the x-axis. It seems to be above the x-axis. Second, as the x values become more and more negative, the y values get smaller and smaller, as we know because this is a function that increases over its entire domain. But what can we learn here about the actual end behavior of this graph as x heads off towards negative infinity? The first thing we might want to notice is that as we go from one x value to another x value that's slightly more negative, there's a jump downward in the y value. But as we keep doing this, that downward jump becomes smaller and smaller until out at the furthest points that we've plotted, -7 and -8, the difference is no longer in tenths, but must be measured in 10,000ths. So to summarize, and as this gap between y values gets smaller and smaller, we have to ask ourselves the question, is there some point in time when that gap reaches 0? Some very large negative x value, for which if I took the next more negative x value, I would see no change in y at all? And also, because these gaps between y values get smaller and smaller, we have to ask ourselves the question, will those y values ever actually get to 0? And there's the possibility that if the y values can reach a value of 0, then maybe we can have negative y values as well. Well, graphically, if we compare the first graph to this graph, it looks like these values are getting closer and closer to 0, but seem to always be staying above 0. So our intuition might tell us that this graph never gets to 0. Our intuition would then also tell us that there would be no minimum y value. But let's look at these two things algebraically. Remember that this function, 3 to the x, for negative values of x, for instance, let's say we have f of -k, where k is some positive number. That's the same as 1/3 to the k. As we make this input value, which is negative, more and more negative, that means that this exponent in the denominator of this fraction gets larger and larger. And since we know the domain of this function is all real numbers, I can keep inserting more and more negative numbers without end. And this exponent will keep getting bigger, which means the denominator of this fraction will keep getting larger. But what does that mean exactly? Well, for example, let's say we were to take an x value of -25. That gives us 3 to the -25th, or 1/3 to the 25th. And an approximation for this value is this number. Is this number quite 0? No, it's still larger than 0. A very little bit larger than 0, but still larger than 0. And if I plug in negative 26 and negative 27, I will still have a value that's larger than 0, but it's going to be smaller than this y value. In fact, consider the case f of negative 200. Just to make a point here, this ends up being 1 over 3 to the 200th power. Well, 3 to the 200th is an incredibly large number, but let's estimate this as a decimal. This is the decimal approximation for that. It's 377 with 95 zeros in front of it. How big is this number? It's unimaginably small, which means unimaginably close to 0, but it is not quite 0, and this is an incredibly important point. The gaps between y values in this graph get smaller and smaller as the x values become more and more negative. The y values become less and less, but since this pattern of 3 to the k always holds, that denominator can get larger and larger and larger, but never so big that 1 divided by that denominator gives us exactly 0. So if we want to talk about the end behavior of the function f of x equals 3 to the x power, as x approaches negative infinity, our function value gets really, really close to 0. We can say that it approaches 0, but it never gets there. This is similar to those cases where we have x approaching infinity and f of x also approaching infinity. The function values will never get to infinity. It's not a number. In a similar way, but through a very different mechanism, in this case, the function values get closer and closer to 0, but never get there. So we get to the key word in this video. This behavior leads to what we call an asymptote in the graph. Specifically, the case of this graph is what we call a horizontal asymptote. I'm going to give a pretty casual definition of horizontal asymptote here. It's a horizontal line that as x values get way out to the boundaries of the domain, the function values, the y values, approach that line, but don't touch that line. This is casual because there are a lot of other cases that you'll explore later in your mathematical career where asymptotes actually can be crossed by the function. But the idea is what happens as our x values are heading out toward negative infinity. So we really only care what's happening way out here. And if it's the case that way out on this part of the domain, the function values are getting very, very close to 0, but not quite getting there, we have a horizontal asymptote. And that asymptote is just this line on the coordinate plane. Let me go back to the graph. So this purple line that I've drawn here is the line y equals 0. It's just the x-axis. As x gets more and more negative, y values get closer and closer to that line y equals 0, but never touch it. Therefore, we have a horizontal asymptote that we can express as the line y equals 0. So we've accomplished our goal of finding the end behavior of this graph. And the end behavior of this graph is getting closer and closer to this asymptote y equals 0. The one place we need to be careful in thinking about asymptotes is that sometimes graphs will look like they have them, but we'll need to look at the algebra to see whether or not an asymptote actually exists there. And here's a good chance to talk about vertical asymptotes. Take a look at our old friend, the parabola. Now, it's certainly true that this curve gets steeper and steeper as we get out towards the ends of the domain. A vertical asymptote will exist in this case if there's some x value this graph will get closer and closer to, but there'll be some point where there are no x values on the graph that are on this line or to the right of that line. Is that the case with the parabola? Well, glancing at this one, it looks like the equation for this parabola is 1/2 x plus 1. This vertical asymptote will exist if there is some x value that we can plug into this equation that will lead to an output that doesn't make any sense. We saw this with the exponential function, because no matter how large we make a negative exponent, that just leads to a larger and larger denominator. But 1 divided by even very large numbers is still greater than 0. Does something similar happen here? Is there an x value we put in that leads to a strange situation like that? And of course, we know the cases that's not true, because the domain of a quadratic function is all real numbers. So there is no x value that I can put in to this equation that's going to lead to an undefined y value, or it's going to lead the equation to do something strange. But you'll see that there are a lot of cases where we do have just this case. Consider this function. This is the function 1 over x. It's a reciprocal function. Just looking at the graph, it appears that in both the third quadrant and the first quadrant, the graph gets closer and closer to the line x equals 0, but something strange seems to happen right there at the y-axis. On the right, the graph goes up very quickly. On the left, it goes down very quickly. In the same way, at the line y equals 0, the graph seems to approach it from above in the first quadrant and from below in the third quadrant, but it looks an awful lot like that exponential function where it never quite gets to that axis. And that's true. In this case, the graph does strange things as it approaches the lines y equals 0 and x equals 0. Let's think about that vertical asymptote for a second. So for the function 1 over x, what happens when x equals 0? Well, f of 0 gives us 1 over 0, which is a completely undefined number. We can't make sense of this number at all. So this is saying that there's actually a gap in this graph at the line x equals 0. Often in cases like this, we'll see a vertical asymptote, because as we saw in the exponential function, for x values very close to 0, this fraction is still defined, but at 0 it's not defined at all. That is the behavior of asymptotes. These values that a graph can approach, but won't quite reach. In the next video, we're going to take a look at a topic closely related to exponential functions, logarithms. We'll see you then. Thank you, everybody.